So there's so many mathematics. Since it is electromagnetic wave theory, it's a lot of mathematics are there. But these are to be considered since fiber is an waveguide. But any equation, any concept, if you not do not follow, you must ask. Right. Anytime you can interrupt me, you can ask. So last times what we have discussed, just quick. I'm just reviewing. We have seen these wave equations from the Maxwell's equations, and we have considered cylindrical coordinate systems. Since fiber is cylindrical, so we should consider the cylindrical coordinate systems R phi z, and these are the wave equations to be solved with boundary conditions. And so you can assume the solution in these forms, right? Amplitude part, phase part. Now wave propagate along z directions is omega t minus beta z. Beta is the propagation constant. So if you know the value of beta, then you can find out the field distribution. That is our intentions. So what we have done it, we have solved the Maxwell's equations. I'm first writing the components. Say polyelectric field R phi z components we have written, and by equating the coefficients on both sides, R component, phi component, and z component, we are getting these three sets of equations, 2, 3, 4. You can see it. It is this ones minus I omega mu HR, H phi, and Hz. And exactly similar way, if you just consider curl of H magnetic field, you see del cross H, that is del D by del T, that is D equal to epsilon E. So you can have these here also in the left hand side, you will have three components, R phi Z components. And here also you can have three components, you see, R phi Z components. So ER, E phi, Hz will be there if you write it. Right, and del T, we have seen this del T can be replaced by I omega. Right, so I omega epsilon into ER will be there. That we have discussed last time. So you can just see it. What we have discussed last time. So e to the power a, say e equal to e to the power I omega t. If we just differentiate it, same thing will be there. E to I omega t, e to I omega t, and I omega components will be there. So that is I omega times E. Right. So that means if it is ER, it will be ER I omega times ER. Similarly, I omega times E phi, I omega like this. Other factor epsilon will be there. So if you write the R phi Z components equating this, you'll get these three equations, 5, 6, and 7, ER, E phi, Ez, similar to HR, H phi, Hz, by taking this Maxwell's equation. Next, you see, if you rearrange these equations, say combining 5 and 3, suppose your aim is to find R phi components in terms of Ez, Hz components. So then ER, you see here it is ER, so H phi contains H phi, Hz. We want to replace H phi by Ez, Hz. So to get H phi, you have to consider the previous equations. H phi equation is this one, 3. So you see that here Ez is there. So combining 5, 3, and 5, you see, combining 3 and 5, that's why I've written it here. 3 and 5, you can have this ER. You can find the value of ER, this ER. And ER will be, you see, minus I by Q square. Right, I by Q square, beta times del Ez upon del R, plus plus omega mu upon R del H by del R. Right. Here we have used these terms Q. All right. This Q actually you'll get when solving these equations. Simply substitute these equations. You get these terms. You'll get it. Omega square mu epsilon minus beta square. So for simplicity, we are using these equations. Omega square mu epsilon, that is actually K square, capital K square. Right. That is also propagation constant. K square. Omega square mu epsilon, K square minus beta square. So Q square is nothing but K square minus square. What is K square? That is omega square mu epsilon. These things are there in electromagnetic theory. It is nothing new. So in terms of ER, Ez and Hz, we are getting I by IQ square. Similarly, E phi also get it I by Q square, beta by R, by combining 6 and E phi. So combining 6, here it is 6, and here it is HR is there. So 2, equation 2 will be there. You can see equation HR2 will be there. You'll get it. These ones you'll get the you'll get the E5. Exactly same way you can have HR H5. Just there is no need of doing the mathematics. Simply, if you just write replace E by H, and with this negative sign, and this factor will be different in this case, omega epsilon by R. Omega epsilon by R will be there. And here it is same as this, only plus it will be minus, and H will be replaced by EZ. So you'll get these ones, right? Actually, HR you can do it also, nothing new. H to get HR, what you'll do it? You have to consider that equations HR equation 2 you have to consider, and here you have to replace E5, and E5 can be replaced. Can be used this 5 6. So in this way, combining 6 and 2 also you can have this the HR. Similarly, you can have H5. So if you now see these 4 equations, you are getting these in terms of EZ and HZ. You see EZ, HZ, EZ, HZ, EZ, HZ, EZ. So that means you are getting transverse components in terms of longitudinal components. That's what we have done it, right? These are the field components through Maxwell's equations. Again, if you just rearrange these equations, you can develop the wave equation for electric field just by rearranging, right? Rearranging, you can have this, you'll get this equation for electric field, and this will get it equation of the magnetic field. Just you have to substitute these values, say H R, say you see it here, how you can have it, I'm telling you, C and D, H R and H5. If you substitute HR and H5, HR and H5 into that previous equations. Previous equations means in these equations, say HR and H5. Here you see it here, 2, 3, 4. You're getting this one. Into C. C means EZ. Here into EZ means here is this one. Here in this. So if you substitute HR and H5 in these equations, then problem is here. Okay. So what will get it? You'll get the equations. This is this one. You'll get it. This equation you'll get it in terms of EZ. That is the wave equation in SI fibers for electric field. Exactly same way. If you consider this, you can have this the wave equation for magnetic field if you replace E by H. Well, if you solve one equation, the similar equation you can have it by E by H, right? So you see it here. This is the standard equation. Del 2 Ez upon del R2 plus 1 by R, del Ez upon del R plus 1 by R square, del Ez upon del phi 2 plus Q square Ez. Q square equal to, we have seen the K square minus beta square, this Q square. So this is the wave equation for electric field in SI fibers. This is the wave equation for magnetic field in SI fibers, right? So actually, electromagnetic wave theory is the electric and magnetic field will be will couple each other. But if you see these two equations, these two are actually independent, right? So you see, but coupling is required, right? Coupling must be required for EZ and HZ. If coupling do not occur, then you see solutions can be obtained by making more solutions can be obtained by making EZ equal to 0 or HZ equal to 0. So if EZ equal to 0, then the mode solution that are obtained, those are called TE modes. TE modes. And if HZ equal to 0, then the mode solution that are obtained, those are called modes, those are called TM modes, transverse magnetic modes. These are T transverse electric modes. When EZ equal to 0 and HZ equal to 0, right? So now, so you can see it here within the fiber, and there will be TE modes, there will be TM modes. Also, there can be another class of modes will be there when both EZ and HZ are non-zero. If EZ and HZ are non-zero, that times you also will get the mode solutions. Those are called actually hybrid modes. That is the main difference between the optical fiber and the conventional waveguide. You will learn many waveguides in wireless communications or microwave engineerings, right? But optical fiber, it's something different. In that sense, here you can have, apart from TE modes, TM modes, you'll get hybrid modes also because it is solid in nature. So when EZ equal to 0, it is TE modes. When AZ equal to 0, TM modes. And when AZ equal to EZ and HZ are non-zero, that times modes are called hybrid modes, and they are labeled as either HE or EH, depending upon the contribution of electric field or magnetic field. If my contribution of magnetic field is more, then it is HE. Contribution electric field more, then EH. So HE or EH. Right. So actually, single mode fiber will see it, and the one mode is propagating. That is actually HE11 mode. Right. That is a hybrid mode, and we'll see this suffix. Why this suffix will come? The suffixes will come. That will see it. So now, actually, at least we have learned the origin of TE modes, TM modes, and hybrid modes. Now, actually, we are trying to find out the condition of bound modes within the fiber. When the suppose bound rays, you have seen it. All the rays are not propagating through the fiber. Similarly, modes also, all the modes will not be propagating through the fiber, or will not be trapped within the fiber. The modes that will be bounded within the fiber, they must satisfy certain conditions. We'll try to find out that condition. To get that conditions, you have to solve these equations. Say for electric field, if you just consider, since you see how many variables are there here. Here R1, phi 2, 2, say 2. Also, if you write Ez in terms of omega and T, so sorry, T variable will be there as well as Z variable will be there. So there are 4 variables are there. So to solve these equations, actually you have to consider the separation of variables method. Right, separation of variables. If you consider that separation of variables method, then you can write the solution of these equations. You see, these equations, you can solve this equation as Ez, that is A, F1R, F2 phi, F3Z, F4T. Because you see, Fz and F4, F3 and F4, these are because the field is I omega t minus beta z. That means T variation is there, Z variation is there. That's why these 2 functions will be there. So there will be 4 functions. R phi to always will be there. R phi Z will be there. R phi Z, it is there. R phi Z. Also, you have to consider the time varying parameters, that is T. So there are 4 functions are there, 4 variables. F1R, F2 phi, F3Z, and F4T. Now this can be reduced to, you have to find out a single variable, then only you can solve it. So you see it here, F3Z and F3A and F4, they can be written as e to the power I omega t minus beta z, right? And also you see this F2 phi, actually this is the azimuthal angles. So since fiber is cylindrical, so if because of the cylindrical, if pi changes by 2 pi, then field will repeat itself. the same thing will be there. So f2 phi will be, you can write it e to the power I nu phi, just like I omega t. So f2 phi will be e to the power I nu phi. Nu is another parameter, right? So if you now substitute all those things, f2 phi, f3z, and f4t, then this you see here it will be simplified. These equations will be simplified because Ez del phi, you see del phi, it is del d2 Ez upon d phi 2, it will be minus nu square. First derivative will be I nu, second derivative will be again I nu whole square. That means I square minus 1, so minus nu square Ez. So del 2 Ez upon del phi 2 will be replaced by minus nu square Ez, right? So if you write, if you substitute all those things, then what will get it? You'll get d2, and also if you write Ez equal to f1r, f2 phi, f3z, f4t, etc., then you see f2 phi already is replaced by these ones, and f3z, f4t, this is these ones, and this will be overall Ez. You see all the terms will contain this one. Right hand side is 0, so this term will be absent. So only f3, f4 will be absent, and f2 is replaced by this derivative, these functions. Only R function will be there. That means f1 will be there. So these equations will be converted in terms of f1. So you see it here, d2 f1 upon dr2. So whenever you see Ez will be replaced by f1. d2 f1 upon dr2 plus 1 upon f1 upon dr plus here will be minus, will be the minus nu square f1 f1 plus q square f1 equal to 0. That's what it is there. You get it. See it here. So q square minus nu square by r square. Here nu square by r square, because r square it is here r square, and this is negative. So q square minus nu square by r square will be there. You see q square minus nu square by r square will be there. I think you know, if you know it, this is the most standard equations in mathematics. This is the second order differential equations, which is the Bessel's equations, Bessel's differential equation. So the solution will be in terms of Bessel functions, right? Directly you can write the equation in terms of Bessel functions. In this context, you should keep in mind, so modes actually, here you see the fiber, we have considered fiber is, you see, it is generally for single mode fiber to 2 to 10 micron, we have seen it, and cladding must be minimum of 125 or 120 microns, 60 microns minimum. So this is 125 microns, but theoretically this cladding can be of infinite, cladding infinite, because you see modes are propagating like these things. You see it here. This is the fundamental mode, this is the mode, and this is the higher order mode. Higher order means several peaks can be there. If a single mode is present, then it is actually Gaussian mode, Gaussian distribution, not Gaussian, similar to Gaussian distributions. That is actually, I told you, this is HE11 mode, right? That is the fundamental mode. And you see, if you investigate these ones, examine this one, there is a peak at the middles, and there is a decay field at the end, decay field at the end, both sides. You see some decay field is there, decay field is there, right? That is called evanescent field, right? Evanescent waves, evanescent wave is there, right? Right, exponential decay is here, that is evanescent field, right? That electromagnetic wave theory. So for each mode, there will be evanescent field will be there in the cladding. And if the cladding is not infinite in the sense, that is because this evanescent field must be 0 before clad air interface. This is core clad, this is clad air. Suppose if it is not cladding dimension is chosen less than 60, then what will happen? The field tail may be outside this cladding. That means there will be leakage of power will be there. So that's why theoretically it should be infinite, but infinite means practically fiber will be just, you see how much dimension will be there if infinite. Then that cannot be considered as a lightweight, etc. right? Fiber is very thin, right? So maximum it can be, I mean, it should be minimum diameter should be 60 to 120 microns. Less than if you reduce it further, then there will leakage of power to the outside mediums. Right. So anyway, in the fields are propagating like these things. There is a peak field at the middles, and decay field will be there. Decay field, or even evanescent field or exponential field will be there in the planning regions. So this is the conditions. Now you see it here. Whenever it is within the core, if you just consider, that means R, radius vector R, R approaches A, R approaches B. If R approaches 0, radius vector approaches 0, means towards the axis, right? You see, then field will be finite. Field will be finite, and if R approaches infinity, if R radius vector approaches infinity, the field must be 0, right? That is the conditions. So if R less than A, that's what, if R less than A, so we can have two kinds of, since it's a Bessel's differential equation, solution will be in terms of Bessel functions. As I have mentioned 120 microns, so the radius, T radius, diameter is D, radius will be 60 microns. So if R less than A, we can consider the Bessel function of one kind, this is J nu, and if R greater than A, another kind of Bessel function will be there, that is K nu, because R greater than A field is exponential in nature. So you have to consider another kind of Bessel function, that is K nu, J nu and K nu. So within the core, when R less than A, we can write the solution in these forms. A Bessel functions will be there, J nu U R. This U actually, you see, some substitution is here. This U, within this, since we have seen this Q square equal to K square minus beta square. So within the core, we can consider K1. So that times U square. You can write U square, that is K1 square minus beta square within the core. Omega square mu epsilon 1. So within the core. So K1 square omega square mu epsilon 1, and within the clad it will be some other values, gamma square will be there, that will see it. So that is actually K J nu U R e to the power I nu phi. This is R functions, this is the F phi functions I nu phi, and this is the T functions, that is the Z functions. So you can assume the solutions in these forms, right? This one, right? And similarly, for magnetic field, we can consider the constant will be different. Other things will remain since B times these ones. Here U square K1 square minus beta square, K1 equal to 2 pi by lambda omega square mu epsilon. So epsilon, if you write refractive index, and so it will come this 2 pi by lambda times N1, refractive index of the core, right? So this is the they are the solutions that you can consider within the core. Similarly, within the clad, when R greater than A, see, it will be, this time Bessel function will be second as a different kind, because field is decaying in nature. So it is K nu WR. It is WR. So omega, we have considered the frequency. So this is K nu WR. Other things same as before, you see. So this is constant. So this is for electric field, this is for magnetic field, right? So these are the solutions inside the core or within the clad, right? Expressions for electric field and magnetic field, Ez and Hz. Now, from the definition of Bessel functions, you see, we can analyze this one. We can find out the condition of bound modes. You see it here. From the definition of Bessel function, this is decaying in nature. So it is K nu WR. Actually, it is e to the power minus WR when omega R approaches infinity. That is from the definition of Bessel functions. Definition of Bessel functions. Anybody, if you have any queries, you can ask anything. So that is omega approaches infinity. This is this ones, and this field must be zero before we have seen it as approaches infinity. I mentioned. So this will be zero. That means this will be zero as r approaches infinity. If r approaches infinity, that means omega must be greater than zero. Omega must be, since you see omega approaches infinity and r approaches infinity, means omega must be greater than zero, right? If omega greater than zero, so omega, right? W, this is W greater than zero. What is W? W it is actually within the clade, just like U within the clade, it is W, actually it is beta square minus K2 square. Beta square minus K2 square. This times K2 is actually 2 pi by lambda times N2. This is the refractive index of the cladding, right? So W square equal to beta square minus K2 square. And so WR approaches infinity, and this will be 0. That means W should be greater than 0. So that means this if W greater than 0 means beta greater than K2. That means you see beta K2, that means K2 it is actually N2 K0 in terms of free space propagation constant. Also you can write it N2 K0, right? That means beta should be greater than equal to N2 K0, right? Similarly, this 2 pi by lambda means it is K0, free space parameter K0. This is K0, so K0 N2, right? So within the core, the field is real, and this is within the clad, right? The field is decaying in nature, but within the core, field is finite, real. So in this case, U square equal to, we know it, U square equal to K1 square minus beta square, and this U must be greater than 0 since field is real. That means you see K1 must be greater than beta. K1 means N0 K1, it is K0. So that means it is K1 corresponds to sorry, N1 K0, N1 K0. Somewhere I've written K1 in the previous slide. You see it here, K1 it is 2 pi by lambda times N1. That means it is this is K0. So this is K0 N1, right? So this K1 must be greater than beta. So if you combine these two conditions, you'll get it. K1 should be greater than beta, should be greater than equal to K2. And in terms of free space parameter and effective index, it will be N1 K0 greater than equal to beta, greater than equal to N2 K0. This is the condition of bound modes within the step index fiber. These are most important things. Generally, if your written examinations is here, that might be asked, find out the condition of bound modes in SI fibers, not from the Maxwell's equations, maybe asked from wave equations. Wave equations means you have to consider that these equations, wave equation for electric field. That means you have to consider this one. There's nothing new, I mean nothing difficulty here. Just you have to consider this one, 4 variables. Now according to simplified, you'll get Bessel functions. And if you describe it within the core and within the clad, what kind of Bessel function will be there? And from the definition of Bessel function, you can have this condition of bound modes. किसी का कोई क्वेश्चन है तो पूछो, किसी का कोई क्वेश्चन तो पूछो. I'm just taking 30 seconds break. किसी का क्वेश्चन है तो पूछो, किसी का कोई क्वेश्चन है तो पूछो. हर्षवर्धन, निश्चय.
Understood, sir.
हाँ?
नहीं sir, I understood, sir.
Okay. So this is the condition of bound modes. Now our aim is to get the value of beta. Then only you can have the field distribution, right? Beta. Also, our aim is to, suppose in a fiber is here, so how many modes will be there in a particular fiber? That we'll see it. Also, we'll see how a single mode fiber can be designed, right? Also, and at the same times, we'll see another important parameter of fiber, that is the V number. Now we can rearrange these parameters so that we can have another parameter of fiber apart from the numerical aperture, that is B number. So if you procure the fiber, you have to mention numerical aperture, you have to mention B number. We'll see it. What is this B number? So I told you initially the mode equations can be solved with the boundary conditions. At the core and clad, you have to apply the boundary condition. Tensor component fields are continuous, tensor magnetic fields are continuous. That means Ez1 minus Ez2 equal to 0, E phi1 minus E phi2 equal to 0. So if you just consider, we have assumed the source in that forms. So if you consider those things, if you just substitute these ones at x equal to a, you'll get these equations. And if I Ez1 equal to E phi2, Ez2, E phi1 equal to E phi2, that means the difference will be 0, right? So these are the equations. You can have it, right? 0. And similarly, you'll get Hz1 minus Hz2 equal to 0, H phi1 minus H phi2 equal to 0. These things we have, the R5 components we have derived earlier. So from that, you can have all these equations, right? And you see, so after getting these equations, you will get 4 equations. You see, one equation, this is 1, this is 2, this is 3, this is 4. So if you now 4 equations with there are how many coefficients are there? There are 4 constant terms are there. You see it here: A, B, C, D, right? A, B, C, D, these 4 parameters are there. So solution can be obtained if you find the determinant of these coefficients equal to 0, determinant. So to get the determinant, you have to write the coefficients. So if you, these things you can have it in Kaiser. I'm just showing it. So there will be coefficients will be there, right? If you write all the coefficients here, coefficients, then you can have these matrix in determinant forms. Determinant, this matrix you'll get it, and determinant of this matrix will give these equations. How we'll get this matrix? You have to write the coefficients. 4 equations are there. So if you write all the coefficients, right, then you can have it, these ones. Just a minute. A, B, C, D. So you see it. Suppose how we're getting these coefficients. I'm playing one example. Say here A, B, C, D is about A, B, C, D, but B is absent, D is absent. So and for A coefficient, it's this one J nu UA, and for C coefficient K nu WA. So that's why you see in this matrix these two A, B, C, D. So this coefficient is here, and B is absent, and D is absent, so 0. Similarly, from the 4 equations, you can have all the coefficients. If you write it, you'll get this matrix. The determinant of this matrix, when you put equal to 0, you'll get these equations, right? Capital JK, this J nu plus K nu plus K1 square J nu, K2 square. What is this J nu? You'll get these ones, J nu primes by this one ratio, and this ratio is replaced by these ones, right? And this is actually complex equations. It is called transcendental equations. Transcendental equations. It's difficult to solve these equations, but numerically it can be solved, right? So anyway, this equation we'll see how these equations can be simplified in future things. Just a minute, and maybe another, we have to consider another slide PPT. This I have to consider. So then this slide is visible. Next PPT, another PPT.
No, sir. It was the modes in SI fiber and the graph. That one slide is visible, sir.
Yes, it is visible. Earlier
Yes,
one
sir.
I have just deleted. This is the second one. So
Yes,
it is visible now. Okay.
Yes.
So after till now we have seen this transcendental equations. We have seen it. That is a complex equation that can be solved with the boundary condition. That can be solved right numerically. Numerically can be solved. Boundary conditions already we have applied. From the boundary we have applied this one. So we are getting the equations. And if you solve the equations, that transcendental equation numerically, then you'll get the value of beta. But since you see these are all function of Bessel functions, so solution will be like these things. Bessel function, if you know it, if you see it is harmonic in nature. If you see this is harmonic in nature. These are the first order Bessel function J0. This is J0. This is J1. All right. Likewise, if higher order Bessel functions will be there, but all are harmonic in nature. You see in this way, and because of these harmonics in natures, so the beta that will be labeled as that will be m roots for a particular value of nu. If you just plot it j nu versus x, j nu x. Say it is an example. I have shown it j nu x versus x. If you just plot it in a MATLAB, you can see it quickly. You can see it. You will get these equations. So J0 for this one, J1 this one, like these things. And for a particular Bessel function, if you see there will be several crossings are there. That means there will be m roots will be there for a particular value of nu. That's why the beta will be labeled as beta nu m's, and accordingly modes that will obtained that will be labeled as nu m's, TE nu m's, TM nu m's, EH nu m's, or HE nu m's. I think it is not quite clear why these suffixes will come. That is because of the nature of the Bessel functions. Bessel functions it can be first order Bessel, second order Bessel, etc. Right, and m comes because of these crossings. So there will be m roots will be there for a particular value of nu. That's why these suffixes will be the modes will be labeled as TEM nu m's, TM nu m's, like these things. They are very similar to, I mean, they can correlate these modes with the rays. If nu equal to 0, right, then the rays are actually meridional rays, right? At that times, the modes are TE or TM, right, for meridional rays. But when nu not equal to 0, that times the rays are actually skew rays, and that times the modes are actually HE or EH, right? So in this way, you can correlate. Anyway, if you just consider these things, nu m's, right, and here also, if you consider just for these TE modes and TM modes, then you have to consider nu equal to 0. So if you consider nu equal to 0, when nu equal to 0, you'll get the equations for these things. It will be simplified. That transcendental equation I have shown it, that will be simplified by these equations. And if you substitute this value of J0 and K0, then you will get these ones, this one. This equation is called the characteristic equations for, you see, for TE0M, TE nu m's. So nu equal to 0, that means this is the characteristic equations for TE0M modes. Similarly, if you consider this and and in that case, you see TE modes EZ equal to 0. This times EZ equal to nu equal to 0 as well as EZ equal to 0. Similarly, here nu equal to 0 as well as HZ equal to 0. Right, then the equations that will get it, these ones, right? Hz equal to 0, that times you get the transverse magnetic waves. So that times modes will be labeled as TM0M modes, TM0M modes. So these are the two important equations for two modes, TE0M modes and TM0M modes, right? For characteristic equations for the two class of modes. Also, you can have another situation when new not equal to 0. I told you new not equal to 0. That means that times the modes will be hybrid modes, either HE or EH modes, right? So you see, okay, that will see hybrid modes. Before that, you see, we'll see this, again, these hybrid modes actually, some degenerated modes will be there, LP modes will be there. Before that, some important thing is this mode cutoff conditions. Suppose you need a particular modes would be absent from the fiber, then that particular mode will be absent. We have seen this for each mode, there is a field tail is there. If this field tail is 0, then that mode will be absent in the fiber. Field tail 0 means that W, we have seen this in the decay field, we have considered W, W parameter we have considered, the W square would be 0. W square 0 means it is beta square minus N2 square K0, that means beta equal to N2 K0. That is beta, not beta 2, beta C, critical value, beta C equal to N2 K0. So that is the mode cutoff conditions, right? And also you can have one important parameter connected with this cutoff conditions. The cutoff condition is the V number or the V parameter or the normalized frequency, these ones. So that is actually U square plus W square times A square, that is defined V square. So if you just substitute the value of U square and W square, see U square it is N1 square K0 square beta square, W square to beta square minus N2 square K0 square. And if you just add it, you'll get it. You see, and substitute the value of K0 to 2 pi by lambda, then you'll get it 2 pi by lambda times A square times N1 square minus N2 square. And you know it, this in numerical aperture we have defined it, we have seen it, that is root over of N1 square minus N2 square, right? So this means it is in numerical aperture square. So that is the most important relations. B equal to K square minus K square A square times numerical aperture B numbers. That is the important parameter of optical fiber. Right. From this V number and numerical aperture, we can design a single mode fiber. I'm coming to that point. Before that, also, you see, this, I told you this V number parameter is related to the cutoff conditions. So some normalized constant is defined here, B, that is called normalized propagation constant. Normalized propagation constant. Propagation constant, that is B, that is actually you see B by definition it is A square W square by V square. It is defined. So if you substitute the W square you have seen it is beta square minus N2 square K0 square. So if you just substitute it, this one, then what will get it? You see, that is W. If you just put it and divide by if you just into K0, if you just divide it, what I say, if you substitute W, that is beta square minus N2 square K0 square, right? So if you whole thing, if you divide it by divide by K0 square, right? K0 square and K0 square, and then what is A square W square by V square, right? And V equal to also K square A square in numerical aperture. If you substitute this one, then if you substitute the value of V and substitute the value of W, then after rearranging, you'll get this beta by K square A0 square minus N2 square by N1 square minus N2 square, right? This will get, this is another, this is the most important parameter also. Here also you can say, you see cutoff conditions, when B equal to 0, mode will be cut off. Beta equal to 0 means beta equal to, you see, this will be this one. That means beta equal to beta C equal to N2 K0. The same way we have seen it earlier. So in this way also we can have it the mode cutoff conditions. Normalized propagation constant 0, that means beta C equal to N2 K0. Right. So just now I've seen this V number, just 1 minute, 1 or 2 minutes. So V numbers, we have seen it's 2 pi by lambda times numeric, this A is the radius, fiber core radius, fiber core radius, A. So V actually 2 pi by lambda times A into numerical aperture, right? And that must be less than equal to 2.405 for SN fiber, single mode fiber. That you must keep in mind. Single mode fiber, that mode it is HE11. When E equal to 1, M equal to 1. HE11, single mode fibers. HE11, right? Single mode fiber. This mode has no cutoff, right? Because if the single mode, if one, there is no power will be there, so energy will be 0. So some power must be there, so that the fundamental mode always will be there, right? So why this typical value 2.405? That is because it's related to the Bessel function. You see it here, the first order Bessel function solution will be in terms of Bessel function. So first order Bessel function crosses this x-axis at 2.405. You see it here. So that's why up to this value V numbers 2.405, this is the for single mode regions. For another crossing is there, then higher order modes will start propagating if it is greater than 2.405. That times TE01, TM01s, HE21s, those values will be there, right? The different values are there. You can see it in the Kaisers, right? So that's what it is here. So we can design a single mode fiber. So by choosing these values of A, lambda, N1 and N2 in such a way that the value V number is coming around less than 2.405, equal to less than 2. Generally it is less than 2.405, then it will be a single mode fiber. That times this mode will propagate, right? So say that if you consider lambda equal to say these values, numerical aperture of these values, V equal to 80. Okay, here I given all examples. Suppose it is asked to design a fiber, right? Just 1 minute. Design a fiber for which say data rate it is 10 Mbps. It is given. That is for nothing role here. Just but sometimes it is given in fiber communications. Data rate is given say 10 Mbps, maybe 10 Gbps, and wavelength is here it is given 10 Gbps. Say lambda it is 1550 nanometers for wavelength. Light is using and numerical aperture is 0.28, right? And V number is given 80. You have to design the fiber, right? Design the fiber means you have to specify the value of N1 core refractive index, cladding refractive index, N2 core radius and cladding radius. So these 4 parameters you have to determine. Then that will be the fiber designs. So if it is this problem, in this problem, numerical aperture given, and you know numerical aperture N1 root over of 2 delta. Delta it is generally 0.01 to 0.02. So you can consider 0.01 for, since V equal to 80 it is given. So blind you can say this is a multimode fiber. Suppose V equal to, if it is 1 it is given, that means single mode fiber. But if it is V greater than 2.405, right, then it is multimode fiber. So multimode fiber, it is delta is this one. If it is single mode fiber, then delta can be, it is 0.001. Because here you see here N1, N2, nothing, no parameters are provided here. Only numerical aperture is provided. So you can assume this solution delta in these ones, right? So from this, you can, if you know the delta, if you know the numerical aperture, you can find out N1. Once you know the value of N1, you can find out the value of N2, right? Because numerical aperture also another relation is here. Numerical aperture, it is root over of N1 square minus N2 square. So if you know the numerical aperture N1, you can find out N2. So you can find out N1, N2. And A also you can find out V number, it is given V equal to 2 pi by lambda times A times numerical aperture. From this you can find out A, but B there is no relation for B. This B actually not this proportion constant. This is the cladding radius, right? So to get B, you have to use that concept that B should be greater than minimum diameter should be 60 microns. Maximum can be infinite, but generally B it should be greater than 60 microns. Right. Means 120, 2 weak and 120 microns. So you can find out all the parameters. That is the design of fibers. Anyway, next time this portion I'll repeat it. But if you have any questions, quickly you can ask. I've taken 5 minutes more. If people are joining late, so 5 minutes to 5 minutes late, we are starting. Any question? हर्षवर्धन निश्चय any questions? हम लोग साइड से कोई क्वेश्चन तो पूछो.
No, sir. I'll just go through the book and I'll ask you next class, sir.
Okay, but this design part is most important. And next time we'll see the how we can calculate the number of modes. You know V number, you know numerical aperture. So from these parameters, how we can calculate the number of modes in a typical fiber. Okay then.